Good afternoon. My name is Gerald Floyd Jr. I'm a student at North Central University. My major is MBA Concentration Computer Science, and today we are going to talk about differentiate formal semantics. This presentation will provide details and comparisons and contrasts of the following semantics: operational semantics, denotational semantics, axiomatic semantics, and additionally, a program will be created and confirmed. This presentation will provide additional information about formal semantics and parallel programming. Particularly, it will focus on the differentiation of formal semantics. Operational semantics. Operational semantics are defined by language by detailing its actions in terms of the operations. The operations include that of machine being used. This requires operations of the machine using a specific description that is perfectly defined. In many cases, a machine will bear little to no resemblance to that actual computer. For example, if a machine is used as a reduction machine, actions may be step by step. This reduces programs by applying operations to values. Operational semantics describe the semantics of a programming language by specifying how an arbitrary program is executed when the operations are completely unknown. Additionally, it can define the behavior of a program by way of an abstract machine. The abstract machine does not have to exist in the hardware, yet it is simple and easily understood. Operational semantics also control how the abstract machine will operate in the program. This can be represented not just by numeric value, but also data value of structure type. So for an example, a programmer may need to use this type of semantics when they're trying to be diverse when it comes to the values, may it be number or data related. Operational semantics are also given reduction rules. These rules specify how the control reduces the constructs of the language to a value. They are given in mathematical notation and similar to the logical inference rules. Inference rules are written, then the line is drawn, then conclusion. Inferences are used to describe the way the control operates and reduces the expression to its value. Additionally, it is possible to implement operational semantics directly as a program to get executable specification. Denotation semantics. So say a programmer wants to know what other type of semantics are out there. They want to kind of contrast and compare. Maybe they're looking for more of a different type of functional related semantic versus mathematical or operational type of semantics. Well, like operational, denotational semantics are related to mathematical objects. They are also known as fixed point semantics. Denotational semantics associates to each program language as well-defined and vastly understood as a well-defined, vastly understood mathematical object. It denotes behaviors of corresponding language constructs, so equal programs can quickly translate into mathematical objects. Each programming language has customized denotational semantics. Each expression can be looked at as a mathematical object, which is a partial function taking into a state of an integer value. Within the integer value, the value of that expression evaluates in the given state. Denotation functions are defined inductively over language constructs. The compounds are defined as the denotation of the parts. Also, denotational semantics prove properties about programs. So for an example, programmer could show that the additional operation of properties whose denotational semantics can be associated. While both denotational and operational semantics describe semantics of programming language, denotational associates semantic values to syntactically correct constructs. For an example, a function that maps an integer arithmetic expression to the value, that val function would be as follows, quote unquote, val colon expression integer. So val, for instance, val open parentheses 1 plus 2 times 5 close parentheses equals 14 in the val 1 open parentheses 1 plus 2 times 5 close parentheses equals 20. Since val maps the first syntactic construct to the semantic value to 14, it denotes the value of 14. And then this is actually the origin of denotational. So a programmer may have questions saying, hey, I understand operational semantics and I understand denotational semantics. I want to see if there are any other semantic out there that's kind of different than the operational and mathematical constructs that denotational and operational have. So axiomatic semantics define the semantics of the program, statement, and a large construct by describing the effect of its execution has on assertions about data that is changed in the program. While denotational, operational semantics focus on describing the programming language, axiomatic goes further and is focused on describing the impact of that execution. The assertions focus on two things that are true before and things that are true after the execution of constructs and assertions. These are also called preconditions and postconditions. So to give a more detail, provide examples. Say a programmer wants to get the details of what the semantics examples are and how they're executed and presented by its value. For an example, quote x colon x plus 1 quote would be, we'll expect that whatever the value x has just before the statement, the value after the execution is one more than the previous value. This can be stated as a precondition that, quote unquote, x equal a before execution, quote, x equal a plus 1 after. The standard writing would be as follows, quote, open bracket, x equal a, close bracket, x colon equals x plus 1, open bracket, x equals a plus 1, close bracket. Also, axiomatic specifications vary by language. For an example, the language C is the form of, quote, open bracket P, close bracket, C, open bracket Q, close bracket. Unlike operational and denotational semantics, axiomatic semantics is a logical proposition. For an example, it states some property about the input and the output. A denotational is a mathematic function, input and output data. Operational is computational, steps that result from processing of the program input. Axiomatic semantics are distinguished by the properties that are produced rather than the meanings of the property. So now we have a programmer, for an example, we have a programmer that's going to use C++ to create a simple program regarding the sum of two numbers. There's a couple of things just observing, looking at this program that can be notated. Notice how there's colons and open and end brackets within the actual statement in the programming of itself. And also the numbers that are being summed up, such as 1 and 2, number 1 and number 2. And in the next slide, we'll go over, there's some steps that could be taken to make sure that this program is accurately processed. So when you create a program and you want to verify if that program is correct, then to identify any errors, there's some steps that can be taken and noted in that error, that situation. For one, each statement, you want to make sure that each statement that is presented as type ends with a semicolon. Another thing that you want to look out for is misspellings, checking the misspellings of the structure or actual programming information that's presented. Another thing is conditional loops. should have one open and one closed bracket. As we previously discussed, we have noted that there was one open and one closed bracket within the programming. And then another thing is just to check the structure, how the line is, how it's all organized, if there are additional spaces where spaces are not needed, things like that can cause errors in the programming. And additionally, a compiler can be ran to be executed to check the program for errors. And for an example, if the program is working in Visual Studio, there's an option to check and execute and compile the program to make sure it is correct. And that concludes the differentiate formal semantics. Thank you for your time.